Hello, I'm Mr. Franklin, and welcome to Conceptual Physics. Remember that as we go along, you can always pause the video, rewind, if you need to go back and review something. Also, don't forget that if you're still learning English, you can also click on the settings on YouTube and turn on the closed captioning, and you can actually see the printed words of what I'm saying as we go along. So, let's jump into today's lesson. Today we're going to be talking about gravity, weight, and mass. Okay, now first thing we're going to look at is, let's talk about gravity. The problem with gravity that most of us encounter when we start to really study it is our existence, our life is, we've always known gravity. And so what it really is and how it works can often be confused with what we think it does. So let's jump into this a little bit. So gravity was defined by Sir Isaac Newton. So this is going to be Newton's definition of gravity. And what he said is gravity is the attractive force between any object with mass. So this is also the definition for weight. So weight is the attractive force between any objects with mass. It's just that when we're on the Earth has mass, I have mass, but the Earth's mass is so strong that I'm stuck to the Earth's surface. If I hold out my marker, it has mass, and if I let go, gravity pulls it to the ground, but it doesn't pull it to me. Why? Because the Earth's mass is so huge, the weight of the object is really defined by the mass of the Earth. So we're going to get into that some more, but what you really need to say is what Newton described was not necessarily what gravity actually is, but more of what is the magnitude of that force. Okay? He said it's the attractive force between any objects with mass. Well, a couple of centuries later, Einstein comes along and tells us a little bit better what gravity is. So what he said was space and time are made out of a single fabric. So if we imagine space and time, all of existence is like a blanket. So I take a blanket, okay? And this fabric is distorted by objects with mass. So I'm going to take the sun and I'm going to put it on my blanket, and it's going to distort or cause the fabric to bend. So much like you can imagine taking this bowling ball and I set it on a blanket, it's going to cause the blanket to bend in the middle, okay? So an object with mass is going to cause this bending. Now, weight, or the force of gravity, is going to be experienced when another object encounters this distortion. The result is going to be the force we call gravity. So if I take the Earth, so we're going to take the Earth here, and I'm going to set it also on this fabric, well, it could roll towards the sun and fall into the hole created by the sun, but the Earth is also moving, and so it basically wraps around in 3D, but it's caught by this hole that the sun is creating, or this bending, this it's almost like a pothole, okay? And the planets get trapped around the sun because of this folding of space, okay? So we're going to focus mostly on this definition. We're going to kind of keep it simple, but we need to understand that all this really does is tell us what the size of this force is going to be. Okay, so with all of this, I keep bringing up the word mass, and there's generally two definitions that people like to use when we talk about mass. The first one is we will say that mass is the amount of stuff in an object. That's kind of a chemistry definition. And it's a simple definition. So if I look at the bowling ball, for example, if I went and started counting what was in it, i.e. I could count the number of atoms, but atoms are made out of things, protons, neutrons, and electrons. I could count all of those pieces, and in doing so, it would tell me basically what the mass is. Now, that's that's how a lot of people in chemistry tend to think about it. In physics, it's a subtler definition, but it's probably more accurate. What we want to think about with mass is it is the measure of inertia. Now, as we understand inertia better, as we grow in our understanding of what inertia really is, it'll make more sense that that's a true definition. But when we did our lab with the cart and we set the weights on it, as we added more weights and we used the same force to push it, it wound up accelerating at a slower rate. It was harder to push. So it had more stuff, it had more inertia. In other words, it had more mass. Okay, so both of these definitions are good to conceptually grab a hold of what mass really is. Okay? What's most important, though, is mass and weight are not the same thing. Okay? This is hard to understand because most of the time when I give you a mass, you only experience that mass on the earth. And so it always has a set weight to it. But the heaviness of the weight that I give you, okay, that is the weight. The actual mass of it is a different number altogether. Okay, so we're going to jump into in the next section here, we're going to talk about Newton's actual equation and how did he say this. Let's talk about things in orbit. So this applies to anything, planets around the sun, satellites around the earth, asteroids around asteroids, moons around planets, that kind of thing. So let's take a look at a satellite. It's orbiting the earth. Now, in our last unit, we talked about uniform circular motion very briefly, and we said that an object that is moving in a circle has a tangential velocity that is perpendicular to the radius, okay, and that there's a force causing it to turn. Well, if an object's in orbit, what is that force? Well, that force, the centripetal force, is actually the force of gravity, if we're talking about an orbiting object, okay? So we can actually use this idea to now decide how fast do we need to make the satellite go in order for it to stay in a circle. Because we know what the force is, because I know what the mass of the satellite is. So I can say mass times VT squared over the radius. I know what the force of gravity is because I know this object's mass. I know the object's mass. I know I can figure out how fast it needs to go based on different parameters and how far out that will mean it has to be. So gravity in this case is the centripetal force. It applies for all situations of objects orbiting other objects. Okay, one other thing. So let's say this is the Earth, but now let's add in a compressed sense, because it's much further than this, much further, not moon. Moon, the Earth and the moon, they're orbiting each other. So the force of the gravity, the Earth is pulling on the moon, so the moon is being pulled by the Earth, but the moon is actually pulling on the Earth as well. Okay? And so while we often think of the moon going around the Earth and the Earth is stationary, what actually happens is they're orbiting each other. Now, the Earth is so much more massive than the moon that the Earth is going to do more of a wobble than, and you're not going to see the motion as much, like especially with our sun. The sun actually moves. It's not stationary. It wobbles, but it's nothing like you see the Earth flying around in circles around the sun, okay? So that's all I have for you today. you can look in Google Classroom, and I'll have your assignment there for you to practice all the stuff we've been learning. Thank you.